It's not what you think. Right now, as you sit there watching this, everything around you feels completely real. Your chair feels solid. Your phone has weight. Your body feels undeniably there. But what if I told you that almost everything you're touching right now is actually empty space? Not metaphorically, not philosophically, physically. And the deeper we go into this idea, the more unsettling it becomes. Because what scientists have discovered about reality doesn't just challenge what things are made of, it challenges whether solid reality even exists at all. To understand this, we have to go back to one of the simplest questions humans have ever asked. What is everything made of? Thousands of years ago, the philosopher Democritus proposed a radical idea that everything in existence could be broken down into tiny, indivisible units he called atoms. But here's what makes that moment so important. Democritus wasn't just guessing randomly. He was reacting to a deeper philosophical problem. At the time, thinkers were arguing about whether reality could be divided infinitely. Could you keep cutting something in half forever? Or was there a fundamental limit? Democritus chose a bold answer. There must be a stopping point. Something you can't divide any further. He called these smallest units atomos, meaning uncuttable. And even though he had no tools to prove it, that idea planted the seed for everything that came later. Centuries passed. The idea was mostly ignored, until science began demanding answers, not just ideas. In the early 1800s, the chemist John Dalton revived the concept of atoms, but for a completely different reason. Dalton wasn't trying to solve a philosophical mystery. He was trying to explain patterns. When he studied chemical reactions, he noticed something strange. Substances always combined in fixed ratios. Water, for example, always formed from the same proportions of hydrogen and oxygen. No matter where you were in the world, no matter how you created it, the ratio never changed. Dalton realized this only made sense if matter was made of tiny units that combined in specific ways, like building blocks. Atoms weren't just an idea anymore. They became the explanation for why chemistry behaves consistently. And that changed everything. For the first time, the invisible structure of matter could be used to predict real-world outcomes. Chemistry became precise, repeatable, reliable. But then came a deeper question. If atoms are the building blocks of everything, what are atoms made of? This question drove scientists forward, not out of curiosity alone, but because their models started breaking. Certain experiments didn't match the idea of atoms as solid spheres. Something was missing. And that's what led Ernest Rutherford to perform his famous gold foil experiment. Rutherford wasn't trying to prove atoms were empty. He actually expected the opposite. At the time, scientists believed atoms were like dense blobs of positive charge with electrons scattered inside, like raisins in a pudding. So he designed an experiment to test that idea. When he fired particles at thin gold foil, he expected them to pass through with only slight deflection. And most did. But a few bounced straight back. This result wasn't just surprising. It was impossible under the existing model. Rutherford later said it was like firing a cannonball at tissue paper and having it bounce back at you. That single observation forced a complete rewrite of atomic theory. He concluded that atoms must have a tiny, dense nucleus, and that everything else is empty space. This wasn't just a new detail. It shattered the idea of matter being solid. And it forced humanity to accept something deeply unintuitive, that the world we experience is not structured the way it appears. But the deeper scientists looked, the stranger it became. Because once the nucleus was discovered, the next question emerged naturally. What are electrons actually doing? Early models imagined them orbiting like planets. It made sense visually. It felt familiar. But experiments began to show inconsistencies. Electrons didn't behave like tiny balls following clear paths. And this is where scientists like Erwin Schrödinger and Werner Heisenberg stepped in. Not because they wanted to make things abstract, but because reality forced them to. They were trying to solve real problems. Why do atoms emit specific colors of light? Why are energy levels discrete? Why can't electrons spiral into the nucleus? The old models couldn't answer these questions. So they built new ones. Heisenberg developed the idea that you cannot know both the exact position and momentum of a particle at the same time. Not because of bad instruments, but because reality itself doesn't allow it. Schrödinger approached it differently, creating an equation that describes how the probability of a particle's position evolves over time. Together, their work didn't just refine physics. It completely redefined what it means to exist. Particles were no longer solid objects with fixed locations. They became possibilities. And this shift had massive consequences. It didn't just change physics. It led to technologies that define modern life. Semiconductors, transistors, computers. The very device you're watching this on exists because scientists accepted that electrons behave according to probability, not certainty. But even then, one question lingered. Why does observation seem to matter? This led to the concept known as the observer effect. Scientists weren't trying to make reality mystical. They were trying to understand why experiments produced different results depending on how they were measured. The answer wasn't consciousness, it was interaction. To measure something at the quantum level, you have to interact with it, often by hitting it with light or another particle. And that interaction changes the system. So what we observe isn't untouched reality. It's reality after interaction. This realization changed how experiments are designed. It forced scientists to account for the influence of measurement itself, and it reshaped our understanding of objectivity. Then came an even deeper layer. Physicists began asking, if particles behave like waves, and waves behave like probabilities, what is the underlying thing that's actually there? This question led to quantum field theory, developed in part by Richard Feynman. Feynman wasn't just solving equations. He was trying to simplify and visualize incredibly complex interactions. He introduced diagrams, now called Feynman diagrams, to map how particles interact. And through this work, a powerful idea emerged. Particles aren't fundamental objects. Fields are. An electron isn't a standalone thing. It's an excitation in an electron field that exists everywhere in space. This insight unified physics in a profound way. It allowed scientists to describe forces and particles within the same framework, and it led to predictions that have been experimentally confirmed to astonishing precision. This is the foundation of the modern understanding of reality. Not solid matter, but interacting fields. Dynamic, continuous, invisible, yet measurable. And while all of this was happening in physics, philosophy never stopped asking its own version of the same question. The philosopher Immanuel Kant argued that we don't perceive reality as it truly is. Instead, we perceive a constructed version shaped by our senses and mental frameworks. He wasn't rejecting reality. He was redefining access to it. And long before him, Plato imagined that what we see is only a shadow of a deeper truth. What's fascinating is that science didn't set out to prove these ideas, but in a completely independent way, it arrived at something strangely similar. A reality that exists beyond direct perception, a structure beneath appearances. So now, when we return to the present moment, everything feels the same. Your chair still feels solid. Your body still feels real. But now you know something more. You know why scientists question these ideas. You know what forced them to rethink everything. And you know how those discoveries shaped the modern world, from chemistry to technology to the very screen in front of you. So the next time you reach out and touch something, and it feels solid, remember this: you're not really touching a solid object. You're experiencing the interaction of fields, the resistance of forces, the outcome of probabilities collapsing into a moment. And in a way, you're touching something that is almost entirely empty.